In this lesson, we want to talk about composition of functions. So at some point when you study functions, you're going to come across this topic known as function composition. And essentially this topic just boils down to plugging one function in as the input for another. That's all it really is. So if you understand function notation, this is really no more difficult. It's just a little bit tedious because you've got to plug some things in. Now related to this topic, we're also going to talk about domain. And we're also going to talk about decomposing functions, which is essentially kind of going in reverse. But we'll get to that at the end of the lesson. So let's just start out by talking about this simple example here, and then we'll get into some stuff that's more complicated. So we have f of x equals 2x minus 5. We have g of x equals 3x squared minus 7. So the first thing you'll come across in your book is this kind of weird notation. Some students call it fog, right? So we have f composed with g. Okay, so that's how that's read. So f composed with g. So this symbol right here is not multiplication. It means composed with, okay? So f composed with g. So let me write that out. This is composed with is what we could say. Let me make that e a little bit better. So f composed with g. So essentially if I wanted to write this in a cleaner format, I can say this is f of g of x, okay? And most of you have already seen this in Algebra 2. Essentially, I'm just working from the innermost set out. So I'm going to take g of x and plug it in for x in my function f of x. That's all I'm doing. So let's go ahead and just try that out real quick. The process is really, really simple. So what I'm going to do is I'm going to say that f of g of x is equal to what? So here's my f of x here. It's 2 times x minus 5. And what I want to do is I want to plug in for x, I want to plug in the function g of x. So g of x is equal to 3x squared minus 7. So that's what I'm going to plug in right there for x. Okay, that's all I'm going to do. So let me scroll down and get a little bit of room going. So 3x squared minus 7, that's what we're going to plug in. Let me just put this up here. So 3x squared minus 7. So what I'll have is f of g of x is equal to 2 times, I'm going to wrap this in parentheses because the 2 is multiplying the whole thing. So 3x squared minus 7, and then minus 5. So all we have to do is simplify this. Pretty simple overall. You're just going to multiply the 2 by the 3x squared. So let's say this is equal to 2 times 3x squared is 6x squared. And then minus 2 times 7 is, of course, 14. And then you have minus 5. To kind of finish this up, all we can do here, we know the 6x squared is not going to kind of simplify or combine with anything. The negative 14 minus 5 is going to be negative 19. So f of g of x is 6x squared minus 19. So very, very simple, very, very easy to get that. Now you might also see them kind of reverse things on you, okay? So you might see g composed with f. So essentially all this is now g is going to be kind of on the outside, and the f is going to be on the inside. So we're taking f of x and now plugging it in for x and g of x. So this is g of f of x, okay? So you've got to think about this as starting on the left side here. This guy's going to be your outer one, and going to the right, that's going to be your inside one, okay? So this is g of f of x. So the order here does matter. So again, all I'm going to do is I'm going to take my f of x, which is 2x minus 5, and I'm going to be plugging that in for x in g of x. So this is going to go in there. So what we'll have here, I'll just put equals here. We're going to have 3 times, and again, for x I'm plugging in, so let me wrap this in parentheses. I'm plugging in my 2x minus 5, and this guy is squared. So let's make sure we square this guy. And then we're going to subtract away 7. Okay, so let's work on this real quick. Now, all of you know at this point, this deep into the course, that we have to expand this, right? We can't just say it's 2x, that quantity squared, minus 5 squared. That is wrong. We need to expand this. So we're going to say 3 times. We're going to use our special products formula to make this quicker. So 2x, that amount squared. 2 would be squared, that's 4. X would be squared, that's x squared. Then we have a minus here, so we'd have a minus. You have 2 times the first term times the second term. Okay, so 2 times 2x is 4x, and then 4x times 5 is 20x. So minus 20x here. And then plus the last guy squared, 5 squared is 25. Close the parentheses, and then you have minus 7 here. Okay, so what do we have? So we're just going to multiply the 3 by kind of each term. 3 times 4x squared is 12x squared. Then minus 3 times 20x is 60x. Then plus 3 times 25 is 75. And then minus 7. So what does this equal here? What is this going to be equal to? Well, we have 12x squared, can't do anything with that. You have minus 60x, can't do anything with that. But then you have 75 minus 7, which is 68. So then plus 68. Okay, so g of f of x is 12x squared minus 60x plus 68. All right, so I'm just going to do one example with this because this is a very easy concept and something you would have covered in Algebra 2. You might also see a number given as the kind of inner set of parentheses. So in this example, we have f composed with g, and then it's of 3, right? So essentially what this means is that we have what? We have f of g of 3. Okay, again, just start with the innermost set and work your way out. So this is g of 3 that's being plugged in for x in f of x. Now, there's multiple ways to do this. You can find f of g of x, which we already know what that is, and then you can plug in a 3 for x in that new function. Or what you can do is you can find g of 3 and then plug that in for x in f of x. So two different ways to do it. Let's just do it both ways so you see that it's the same. So let's find g of 3 first. So what is g of 3? Just plug in a 3 for x there. 3 squared is going to be 9, so you'd have 3 times 9 minus 7. 3 times 9 is 27, and 27 minus 7 is 20, okay? So g of 3 here is 20. So really what I have is f of 20, okay? Because g of 3, the result is 20. So what is f of 20? Well, I go to my f of x, my function here, and I just plug in a 20 for x. So it would be 2 times 20, okay? 2 times 20 minus 5. 2 times 20 is 40. 40 minus 5 is 35. Okay, so that's my answer. F of 20 is 35, so that tells me f of g of 3 is 35 as well. Now, so we already found that f of g of x was 6x squared minus 19. So if I said, what is f of g of 3? So I can just take this f of g of x, I already know what this is, and I can just plug in a 3 for x. So I can say this is equal to 6 times, plug in a 3 for x, that's going to be squared, then minus 19. We should get 35 if I got the right answer, right? So 3 squared is 9, so I'd have 6 times 9 minus 19. 6 times 9 is, of course, 54. So you'd have 54 minus 19, which is 35. Okay, so you get the same answer either way. So you can either do it this way, find f of g of x first, and then plug in kind of the value you're given. In this case, it's 3, so we got a result of 35. Or we can do it this other way, where we find g of 3 first, and then we plug that result in, which in this case was 20, for f in the original function. Okay, so two ways to kind of do that. I'm not going to do another example of this because it's really easy. We want to move on to something more complicated, known as finding the domain. So let's look at finding the domain for a composite function. So this is kind of a really tricky thing. So we're going to spend most of our time in this lesson on this because the other parts are really, really easy. First and foremost, when we consider the domain of a composite function, we need to do two things, okay? The first thing is we need to consider the domain of the inside function. So this is the function that's being plugged in as the input for the outer function. Okay, so that's very important. A lot of students mess that up. They forget to do it. So that's the first thing. Then we need to think about the domain of the new composite function that is built. Okay, so we're going to look at both of those, and then we're going to state the domain of this composite function that we're building as the intersection of the domain of the inside function and our composite function. We don't need to think about the outside function, and I'll show you that as we kind of move on, okay? So remember, when I say intersection, I mean the overlap between the two. So this means it must be valid in the domain of the inside function and also valid in the domain of the new composite function that we've just created. I just want to say this again, finding the domain for a composite function is really tricky, and it's something that you'll probably struggle with when you first see it, okay? So in this particular case, if we think about the domain, whether I have f composed with g or g composed with f, it's going to be all real numbers in each case. And the reason for this is, if we think about the inside function, well, for f composed with g, this guy is f of g of x. Well, the inside function here is g of x, and it's all real numbers, right? So I can plug in anything here for x and square it, multiply it by 3, and then subtract away 7 from the result. There's no problem there. When I plug this in here, okay, I know that I end up with a result that's what? It's 6x squared minus 19. In this new function that we've created, there's no restrictions on x as well. So the domain here for this guy is all real numbers, and it's going to be the same thing with this guy as well. When we look at g of f of x Remember, this was 12x squared minus 60x plus 68, okay? So when I look at f of x, it's 2x minus 5. That's all real numbers. Then when I look at the composite function we create, the 12x squared minus 60x plus 68, that's all real numbers as well. So the domain in each case here, we could just say the set of all x such that x is a real number. Okay, you could do it like that. Or again, you could do it in interval notation. Again, for each one, it's the same. So from negative infinity to positive infinity, all real numbers. All right, let's look at an example that's a little bit more complicated now. So we have f of x equals 1 over x, and we have g of x equals the square root of 5 minus x. So let's do f of g of x, and then let's determine the domain, and then we'll flip it around and look at g of f of x, and we'll look at the domain of that as well. So when we think about this, f of g of x is quite simple to find. So g of x is here. It's the square root of 5 minus x. F of x is here. So I'm just going to plug g of x in for x in f of x. That's all I'm doing. So I would have 1 over, again, I'm plugging in for x. I'm plugging in the square root of 5 minus x. So that part's very, very simple. Something you've done, again, in Algebra 2. Some of you even would have done it in Algebra 1. But finding the domain is a little bit tricky. So we want the intersection, again, for the domains of the kind of inside function and then of the newly created function. So this is f of g of x. You could even name it as something new. You could say this is h of x if you wanted to. And I'll kind of get to that in another example. I'm going to leave that off for now because I don't want to confuse you. So what's the domain for the inside function, the g of x? So g of x, what's the domain? Well, if I think about the square root of 5 minus x, what can I do? I can't take the square root of a negative, so I would just take this 5 minus x, this radicand, and I would say that it has to be greater than or equal to 0. Pretty easy to solve this. Just add x to both sides of the inequality, and you would have 5 is greater than or equal to x, okay? Or you could say x is less than or equal to 5. So let me erase this and say that we know that x needs to be less than or equal to 5. So that's my restriction here on the domain for the inside function. Now, when we look at the newly created function, the f of g of x, we have 1 over the square root of 5 minus x. So we have a radical, the same one. So we have the same restriction here that x needs to be less than or equal to 5. So that's still there. So for the domain of f of g of x, we have that same restriction that x needs to be less than or equal to 5. But we have something else that we need to consider. We have division here, and we have a variable in the denominator. So we need to make sure that something that gets plugged in for x doesn't create a 0 denominator, right? We don't want to divide by 0 that's undefined. So where would the denominator be equal to 0? Well, what I can do is I can say, where is the square root of 5 minus x equal to 0? Well, there's a lot of ways to think about this. We know the square root of 0 equals 0 if this becomes 0. So I could just say 5 minus x equals 0. Just solve that. I would just add x to both sides of the equation and find that x equals 5. So if I plugged in a 5 there, 5 minus 5 is obviously 0. Square root of 0 is 0. So 1 over 0 will be undefined. So what I have to do here is further restrict the domain for the composite function, the newly created function that we just built. And I have to say that not only does x need to be less than or equal to 5, x needs to be strictly less than 5, okay? And so what happens is I want the intersection of these two. This one right here is more restrictive, right? So this contains all the same numbers as this one except for 5. So I've got to go with this one as the domain for this f of g of x. So again, the intersection of the two. So let me erase this, and we'll just state our domain here. Our domain is going to be from negative infinity up to but not including 5. Okay, so that's the domain. You could also say that it's the set of all x such that x is less than 5, right? And it's strictly less than. If you put less than or equal to, that would be wrong. Okay, so now that we understand that, again, we've got to consider the inside function and the newly created composite function. So this whole thing, this guy that we're looking at here, that's what we're looking at. Now, a common mistake is to look at this f of x function. This is a different function, okay? So students will start going, okay, well, x can't be 0. Well, x can be 0, right? If I plugged in a 0 there, I'm fine. 5 minus 0 is 5. I can take square root of 5. That's not an issue. Also, I can plug in a 0 here, right? It's the same thing. So don't look at this f of x function, this outer function in this kind of composite thing that we're building. You need to look at the composite function as a new function, okay? Something that we are creating based on taking the inside function and plugging it in for x in the outside function, okay? So I know that can be confusing at first, but after you work enough examples, it just becomes something that is kind of second nature for you, okay? So let's look at the other way around now. Let's think about g of f of x. So what is this now? So now I'm going to take this f of x, which is 1 over x, and I'm going to plug it in for x in this g of x, again, square root of 5 minus x. So this guy is going in right there. Now, this one will be a little bit more complicated. So we will have the square root of 5 minus, again, for x, I'm plugging in a 1 over x. Okay, so now let's think about the domain. And again, this one will be slightly more complicated. So my domain. Now the inside function is 1 over x, right? It's the f of x. So now I'm going to restrict this to where x cannot be 0, because 1 over x, we know that the domain restriction there would be x can't be 0 because we can't divide by 0. So x cannot be 0. Okay, that's my domain restriction. Now, in this particular one, I have that 5 minus 1 over x is underneath the radical. Okay, so essentially I know that I want this guy to be non-negative. And so what I'd have to do here is say that 5 minus 1 over x needs to be greater than or equal to 0. So this is a rational inequality. It's an easy one, but we do need to solve it and figure out what our restrictions are going to be. So I'm going to write this as a single fraction. So essentially I'm just going to multiply this guy right here by x over x. And so I'll have 5x minus 1 over the common denominator of x. This is greater than or equal to 0. Okay, so now what I want to do is find the critical values. You guys all should remember this. So I know that one of them would be what makes the denominator 0. So here it would just be x, set that equal to 0. So I know 0 is a critical value. And I know because it makes the denominator 0, it's going to be excluded from the domain. And we already know that because it was excluded from the domain before. Okay, so nothing new there. Then we have our numerator. So we have our 5x minus 1, set that equal to 0, get our other critical value. So add 1 to both sides. We get 5x equals 1, divide both sides by 5. You get x equals 1/5. Okay, so this critical value will actually satisfy this guy, right? Because if I plugged in a 1/5 there, 5 times 1/5 is going to be 1. 1 minus 1 is 0. 0 over a non-zero number would be 0. 0 is greater than or equal to 0 is true. Okay, so 1/5 is okay. Now, what we want to do is take these two numbers. So we have x equals 0 and then 1/5. And we want to kind of think about this. Again, you've got to kind of test values in the intervals that you create with this. So one interval is going to be from negative infinity up to but not including 0. The other interval is going to be between 0 and 1/5. And then the other interval is going to be greater than 1/5 out to positive infinity. Okay, so those are the intervals. So if I look at the inequality we started with, it was 5 minus 1 over x is greater than or equal to 0. Okay, so let's choose something that's less than 0. Let's just choose -1. It's pretty easy to work with. So if I did 5 minus 1 over -1, I could really write this as plus negative if I want. Is this greater than or equal to 0? Yes, it is, right? -1 over -1 is positive 1. So this would end up being 6. 6 is obviously greater than or equal to 0. So this would be true, right? So values that are less than 0 would work. Between 0 and 1/5, we need to find something that we can plug in there. Let's just go ahead and use 1/10. So if I plugged in a 1/10 there, I'd have 5 minus 1 over 1/10. Is that greater than or equal to 0? 1 divided by 1/10 is the same thing as 1 times 10. So this would be 5 minus 10. You know that would be -5. -5 is not greater than 0. It's not equal to 0. So this would be false. Okay, nothing would work in that interval. In the last interval, I could just choose, let's say, positive 1. So let's put 5 minus 1 over 1. This would, of course, be 1. 5 minus 1 is 4. 4 is greater than 0, so this is true. Okay? So now we know what our domain is going to be. We know that 0 is excluded, right? So 0 is excluded. We know that values that are less than 0 would work. So from negative infinity up to 0. We know that values between 0 and 1/5 do not work. And then we know that values greater than 1/5 and also including 1/5 would work. So I put a bracket there, 1/5 out to positive infinity. So let me just copy this. So for my domain, I can just list it out like this. We'll say from negative infinity up to but not including 0, right? 0 is not included. Then the union with, we have that 1/5 is included and then anything larger. All right, let's take a look at another one. So we have f of x equals 2 over x minus 1, and then g of x equals 3 over x. Okay, so let's start with f of g of x and see what we get. So again, I'm just going to plug g of x, which is this 3 over x, in for x and f of x. That's all I'm doing. So 2 over, I would have 3 over x and then minus 1. Okay, so you can simplify this guy if you want. You can multiply, it's a complex fraction. You can just multiply the numerator here by x and the denominator here by x. And let me scroll down and get some room going. This would give me what? It would give me 2x in the numerator over x times 3 over x would be 3, and then minus x times 1 is just x. So you get 2x over 3 minus x. Now, if I want to think about the domain of this guy, again, if I go back up, the inside function g of x equals 3 over x. So that's not defined where x is 0. Okay, so x can't be 0. When I think about the kind of new function that I've created, so let me erase this and just kind of drag this up so I can fit all this on the screen. When I think about this guy right here, this 2x over 3 minus x, well, I can say that 3 minus x can't be 0, right? So I could just solve 3 minus x equals 0, add x to each side of the equation, and I find that x is equal to 3 there, right? So x can't be 3 as well. So x can't be 0 coming from the inside function, and x can't be 3 coming from our composite function, the one that we just formed. So let me erase this, and I'll officially write that real quick for you. So the domain, you could write it using this format if you want. You could say the set of all x such that x does not equal 0 or positive 3. Okay, set builder notation, that's fine. Or if you want, you can use interval notation, which is a bit longer here. So from negative infinity up to but not including 0, the union with, you'd have anything larger than 0 up to but not including 3, and then the union with anything larger than 3. Okay, so kind of gets really long with interval notation for this problem. All right, so 2 common mistakes again for this type of problem. The first one is forgetting to find the domain of the inside function. So g of x was the inside function. If we forgot about the domain here, you wouldn't have thought about 0 being restricted from the domain. So that's the common mistake. Then the second mistake, again, is to think about the outer function, the one we plugged into, the f of x. A lot of students will say, okay, I've got f of x equals 2 over x minus 1. You'll see them say, okay, well, x can't be 1 there, and then they restrict that from the domain as well. That's not restricted from the domain here. We're only considering the new composite function that we formed and the inside function, right, the one that we plugged in. Okay, that's all we need to do. Now, let's look at g of f of x. So let's look at g of f of x now. Okay, so again, all I'm going to do is I'm going to take f of x, which is 2 over x minus 1, this guy right here, and I'm just going to plug it in for that guy right there. So you'd have 3 over, you'll have 2 over x minus 1. Okay, so how can we simplify this? Again, we've got a complex fraction. So what we can do is we can multiply by x minus 1 over x minus 1. So what we're going to get is what? Let's scroll down and get a little bit of room going. We'll have 3 times the quantity x minus 1 in the numerator over, in the denominator, the x minus 1s are going to cancel, so you would just have your 2 there, okay? So you get 3 times the quantity x minus 1 over 2. So let me erase this real quick, and let me kind of scooch this up. And I want to think about the domain with you. And I'm going to show you a little trick on this one, because a lot of people get confused with this. So let me kind of go through this way, and then I'll go through it a different way. All right, so the first way, I'll say that the domain is what? What did we plug in? We plugged in f of x. F of x is 2 over x minus 1. We know there that x minus 1, if we set that equal to 0 and we solved it, we would get that x equals 1. So we know that 1 is restricted from the domain of this inside function. So x can't be 1. Now, In the new function that we've created, are there any restrictions on x? Well, even if I multiply this out and say it's 3x minus 3, 3x minus 3, no, right? This is a linear equation, right? So we have 3x minus 3 over 2. There's nothing I can't plug in for x there. So the domain for this guy is just going to be all real numbers except for 1. So again, I can say that it's the set of all x such that x doesn't equal 1. Or you can use your interval notation. Again, doesn't matter. From negative infinity up to but not including 1. And then union with anything larger than 1. Okay, so you can do that as well. Now, let me think about a different way to kind of show this to you. Your book might show you kind of this technique. We already know the domain, so we don't need it up there anymore. Let's say I take my outer function, my g of x, and I write it. So I have my 3 over, and then I have x. So instead of writing x, I'm just going to put f of x here. I'm just going to put f of x here. Okay, so I have 3 over f of x. Now, let's consider the fact that this guy was plugged in. Okay, this guy was plugged in. So we know that we first need to find where f of x is undefined, right? So we already know that it's undefined where x is 1. So we've already restricted that from the domain. So x can't be 1. Okay, so now we move on and say that in this form, we know that f of x can't be 0 because it's in the denominator, okay? So let's think about that. F of x is 2 over x minus 1. We would say, where is this equal to 0, okay? Where is this equal to 0? Well, if I think about that for a while, I think about the fact that if I'm dividing here, how can I get a result of 0? Well, I've got to have a 0 in the numerator, and I've got to have a denominator that's not 0. So it is actually not possible to get a solution here. You can go through and try, you will not, because 2 divided by x minus 1 will never give you 0, okay? You can't plug in a 1 for x, we already know that, but you can plug in anything else that you want, and it doesn't matter what you plug in, you will never get a 0 over here because, again, you need 0 in the numerator and a non-zero denominator to get a result of 0. So what that tells you is that there's no restrictions here on this kind of newly created function, which will be 3 over f of x. And again, f of x was 2 over x minus 1. And again, we multiplied the numerator by x minus 1 and the denominator by x minus 1. And we found that this was 3 times the quantity x minus 1 over just 2, right? So that's what we got. And again, you can write that as 3x minus 3 if you want, over 2, doesn't matter. But again, the domain, we know that this is from negative infinity up to but not including 1, and then the union with anything larger than 1. Okay, so either way you want to look at that. I know that the way that I just showed you, where you kind of say, you know, the f of x there, which is being plugged in for x, can't be equal to 0. If you look at it that way, that's another way to kind of go about it. All right, let's look at one more of these, and then we're going to get into decomposing functions, which is really easy. Okay, so this is kind of the hard part. If you're good to go on the domain, you're good to go with everything with this topic because it's really, really simple. And the domain just takes a few tries to kind of wrap your head around what you need to do. But again, if you just remember, you want the inside function, you want the newly created function, you want to look at those two domains, and you want the intersection or the overlap between those two domains. Okay, that's how you get the domain of your composite function. So here we have f of x equals 1 over x squared plus 2x minus 35. We have g of x equals 1 over x. So in the interest of time, I'm just going to do f of g of x. So I'm just going to do f of g of x. So let's just start with that. So we have 1 over, and I'm plugging in a g of x everywhere there's an x. So I'm plugging that in here and here, okay? So I would have what? I would have 1 over x, that quantity squared, plus 2 times 1 over x, so it's basically 2 over x, and then minus 35. Okay, so that's what I'd have there. Now, if you want to simplify this quickly, you can kind of square this first and say that this is 1 squared, which is 1 over x squared. You can go through and you can multiply the numerator and denominator by x squared, right? Because this is just a complex fraction. And you have x squared, x, no denominator there. So I'm just going to multiply this by x squared and this by x squared. And what I'm going to get is x squared in the numerator over. In the denominator, the x squareds would cancel, so you'd have 1 there. Then plus, x squared would cancel with x and give me x. X times 2 is 2x. And then minus, you'd have x squared times 35, which is 35x squared. So this is our f of g of x. So let me erase this. Let me just kind of move this up here. This is our f of g of x. Now, you can think about the domain, again, in a few different ways. You can first look at g of x. We know that it's 1 over x, so obviously x can't be 0. And then you can look at this composite function here, and you can say, okay, well, 1 plus 2x minus 35x squared, that can't be 0 because that's in the denominator. Okay, so you can do that as well. So let's do it that way. So let's go through and say that 1 plus 2x minus 35x squared, where is that equal to 0? We're going to restrict those values. To make this easier, to put it in a format that we're used to, go ahead and divide everything by -1. That's just going to change the sign of everything. So this would be minus, this will be minus, this will be plus. It has no effect on 0, right? So we would have 35x squared minus 2x minus 1 equals 0. You can factor this if you want to, or you can solve it with the quadratic formula, whatever you want to do. It's going to factor. So I know it would be what? It would be 35 is either going to be 35 times 1 or 5 times 7. It's not going to be 35 times 1, so we're going to have to do 7x and 5x. And then for -1, that can only come from a +1 times a -1. So you really just have to work out whether it's +1 here and -1 there, or the opposite. So this way it would be -7x and then +5x. And that's exactly what we want, because -7x plus 5x would be -2x. So that's good to go there. Okay, so now I would just set these two equal to 0 and solve. So 7x plus 1 equals 0. Subtract 1 away from each side. You get 7x equals -1. So 7x equals -1. Divide both sides by 7. You get x equals -1/7. Okay, so that's one value we're going to restrict. So let's erase this. And we'll just kind of keep this for a second. Then the other guy is 5x minus 1 equals 0. Add 1 to both sides. You get 5x equals 1. Divide both sides by 5. You get x equals 1/5. Okay? So x equals -1/7 and then 1/5. All right, let's erase all this. Okay, so x can't be 0. We know that from the inside function. And then also x can't be -1/7 or 1/5. So let's write our domain. So let's write our domain. And we probably want to write this one down here because it's going to be a little bit lengthy. So I'll start by writing it in set builder notation, the set of all x such that x cannot be equal to 0, 1/5, or -1/7. Okay? So in interval notation, this is going to be from -infinity up to but not including -1/7. And then the union with, you'd have anything larger than -1/7 up to but not including 0. And then you would have the union with anything larger than 0 up to but not including 1/5. And then you'd have another union with anything larger than 1/5. Okay, so this one is really long when you write that in interval notation, but that's generally how I like to do it. All right, let's wrap up the lesson and think about something that's pretty easy overall. It's called decomposing functions. This is another topic you're going to see in this section, and it's very important because when we get to calculus, we're going to have to treat a function as a composition of two functions. So in other words, when we compose functions, we're going to compose two functions to form a new function. When we decompose functions, we're going to express it as the composition of two functions. You're going to see this right away in calculus. Okay, so it's going to be very important. So now here's where I'm going to kind of change the name a little bit. You've seen that we created a new function, but you can give this new function a name. A lot of times you're going to call it h, right? So we'll say h of x equals f of g of x. And this is equal to 1 over 2x minus 3. So essentially, we've already done the function composition, and we have the result of that, and we want to decompose it, okay? So we want to find f of x and g of x. So very, very simple process. So h of x is equal to f of g of x. And this is equal to 1 over 2x minus 3. Okay, so lots of different ways to kind of think about this. But essentially, if you really think about what could be the outer function, what could be the inner function, well, I could have plugged this guy right here in for x in 1 over x. Okay, so the outer function, the f of x, would be 1 over x. And the inner function, the g of x, would be what? It would be 2x minus 3. Okay, so if I took 2x minus 3 and I plugged it in for x in this 1 over x, I would get 1 over 2x minus 3. So that would be an answer here. So find f of x and g of x. F of x would be 1 over x. G of x would be 2x minus 3. All right, let's look at another one of these, and then we'll just kind of wrap it up. Very easy topic overall. So a lot of times they give you these, they're very obvious. So h of x equals f of g of x. This is the cube root of x squared minus 2x minus 1. find f of x and g of x. Well, we know that this guy right here would be the inside, what's being plugged in for x. And the outer would just be this kind of cube root operation. So essentially the f of x, the outside guy, would be the cube root of x, okay? So that's my outer one. The inner one, the g of x, what I'm plugging in for this x here is just this right here, this x squared minus 2x minus 1, okay? So this topic is very, very simple.